Wow, it's so great to be here. I just realized I forgot something. I actually did.
It's on this.
Oh, where is it? Where is it? What? This is what happens when you don't rehearse. Up. Don't go anywhere. Hello? Anybody back here? I bet this has, when you have it, could you bring it out to me? I bet this has never happened before. Oh, thank you. Ladies and gentlemen, Mackenzie. Mumbai. So much happening. So much happening. This is, as you know, India, very, very dear to the world's computer industry, central to the IT industry. At the center, at the core of the IT of just about every single company in the world. My industry, your industry, that we've built over the last several decades is going through fundamental change, seismic change, tectonic shifts. Let's talk about that today. But before we start, let me thank all of our partners. There are so many of you working with, yeah, please, thank you. Our incredible partners that we're working with here in India to transform the IT industry together. And so I'm delighted that all of you have joined us today. There are two fundamental shifts that are happening at the same time. This hasn't happened since 1964, the year after my birth. It wasn't because of my birth, but in 1964, the IBM System 360 introduced the world to the concept of IT, the IT industry as we know it, introduced the idea of general purpose computing. They described a central processing unit, a CPU, I/O subsystems, multitasking, the separation of hardware and application software through a layer called the operating system. IBM described family compatibility for applications so that you could benefit by the install base of your hardware to run your software over a long period of time. They described architectural benefit across generations so that the investment that you make in software, the investments you make in using the software is not squandered every single time you buy new hardware. They recognized in 1964 the importance of install base, the importance of software investment, the importance of building computers that run the software. Architecture discipline, all described in 1964. I've just described today's computer industry. The same industry that the India IT industry was built from. General purpose computing as we know it has existed for 60 years until now. For the last 30 years, we've had the benefit of Moore's Law. An incredible phenomenon. Without changing the software, the hardware can continue to improve in an architecturally compatible way. And the benefits of that software doubles every year. As a result of doubling in performance every year, depending on what your applications, you're reducing your cost by a factor of 2 every single year. The most incredible depreciating force of any technology the world's ever known. By depreciation, cost reduction, it made it possible for society to use more and more of IT. as we continue to consume IT, as we continue to process more data, Moore's Law made it possible for us to continue to drive down cost, democratizing computing as we know it today. Those two events, the invention of the System 360, Moore's Law with Windows PC, drove what unquestionably one of the most important industries in the world. Every single industry has subsequently been built on top of it, IT. But we know now that the scaling of CPUs has reached its limit. We can't continue to ride that curve, that free ride. The free ride of Moore's Law has ended. We have to now do something different, or depreciation will end. And we now will not enjoy depreciation, but experience inflation, computing inflation. And that's exactly what's happening around the world. We no longer can afford to do nothing in software and expect that our computing experience will continue to improve, that costs will continue to decrease, and continue to spread the benefits of IT and to benefit from solving greater and greater challenges. We started our company to accelerate software. Our vision was there are applications that would benefit from acceleration if we augmented general purpose computing. We take the workload that is very compute intensive and we offload it and we accelerate it using a model we call CUDA, a programming model that we invented called CUDA that made it possible for us to accelerate applications tremendously. That acceleration benefit has the same qualities as Moore's Law. For applications that were impossible or impractical to perform using general purpose computing, we have the benefits of accelerated computing to realize that capability. For example, computer graphics. Real-time computer graphics was made possible because of NVIDIA coming into the world and make possible this new processor we call GPUs. The GPU was really the first accelerated computing architecture running CUDA, running computer graphics, a perfect example. We democratized computer graphics as we know it. 3D graphics is now literally everywhere. It could be used as a medium for almost any application. But we felt that long-term, accelerated computing could be far, far more impactful. And so over the last 30 years, we've been on a journey to accelerate one domain of application after another. The reason why this has taken so long is simply because of this. There is no such magical processor that can accelerate everything in the world. Because if you could do that, you would just call it a CPU. You need to reinvent the computing stack from the algorithms to the architecture underneath and connect it to applications on top. In one domain after another domain, computer graphics is a beginning, but we've taken this architecture, CUDA architecture, from one industry after another industry after another industry. Today, we accelerate so many important industries. Cullitho is fundamental to semiconductor manufacturing, computational lithography, simulation, computer-aided engineering, even 5G radios that we've recently announced partnerships with, that we can accelerate the 5G software stack, quantum computing, so that we can invent the future of computing with classical, quantum, hybrid computing. Parabricks, our gene sequencing software stack. QVS, one of the most important things every single company is working on, is going from databases to knowledge bases so that we can create AI databases. Using QVS, we can create and vectorize all of your data. QDF, data frames. Data frames is essentially another word for structured data. SQL acceleration is possible with QDF. In each one of these different libraries, we're able to accelerate the application 20, 30, 50 times. Of course, it takes a rewrite of software, which is the reason why it's taken so long. In each one of these domains, we've had to work with the industry, work with our ecosystem, software developers and customers, in order to accelerate those applications for their domains. cuOpt, one of my favorites, combinatorial computing application, a very compute-intensive application, for example, the travel salesperson problem. Every supply chain, every driver-rider combination, those applications could be accelerated with cuOpt, incredible speed up. Modulus, teaching an AI the laws of physics, not just to be able to predict the next word, but to be able to predict the next moment in time of fluid dynamics and particle physics and so on and so forth. And of course, one of the most famous application libraries we've ever created, called cuDNN, made it possible to democratize artificial intelligence as we know it. These acceleration libraries now cover so many different domains that it appears that accelerated computing is used everywhere. But that's simply because we've applied this architecture, one domain after another domain, that we've covered just about every single industry. Now, accelerated computing, or CUDA, has reached the tipping point. Several years ago, about a decade ago, something very important happened. And most of you have seen the same thing. AlexNet made a gigantic leap in the performance of computer vision. Computer vision is a very important field of artificial intelligence. AlexNet surprised the world with how much of a leap that it was able to produce. We had the benefit of taking a step back and asking ourselves, what are we witnessing? Why is AlexNet so effective? How far can it scale? What else can we do with this approach called deep learning? And if we were to find ways to apply deep learning to other problems, how does it affect the computer industry? And if we wanted to do that, if we believe in that future and we're excited about what deep learning can do, how would we change every single layer of the computing stack so that we could reinvent computing altogether? 12 years ago, we decided to dedicate our entire company to go pursue this vision. It is now 12 years later. Every single time I've come to India, I've had the benefit of talking to you about deep learning, had the benefit of talking to you about machine learning, and I think it's very, very clear now the world has completely changed. Now let's think about what happened. The first thing that happened, of course, is how we do software. Our industry is underpinned by the method by which software is done, the way that software was done.